Okay, week 9, chapter 9. We learn about design of experiments and ANOVA. In business, I doubt you will be designing experiments, but ANOVA is a useful tool, especially when we start interpreting regression results. So let's start by defining different parts of an experiment. The response variable is the variable of interest to be measured in the experiment. We also refer to the response as the dependent variable. Typically, the response-dependent variable is quantitative in nature. Factors are those variables whose effect on the response is of interest to the experimenter. Quantitative factors are measured on a numerical scale, whereas qualitative factors are those that are not naturally measured on a numerical scale. Factors are also referred to as independent variables. Factor levels are the values of the factor used in the experiment. The treatments of an experiment are the factor level combinations used. An experimental unit is the object on which the response and factors are observed or measured. So here are a couple of examples of designed experiments. Say we have 30 stores that are randomly assigned one of 4 levels for store display, which would be our independent variable. We want to see the effect on sales, which would be our dependent variable. So that's one example. Second one, if we had 200 consumers that are randomly assigned one of 3 levels of brands of juice, that would be the independent variable. And we want to study the reaction, or let's say taste, of these juices and their opinions on it. That would be the dependent variable. Now, let's look at randomized experiments. So a completely randomized design is a design for which independent random samples of experimental units are selected for each treatment. Experimental units, or subjects, are assigned randomly to treatments. Subjects are assumed homogeneous, one factor or independent variable, 2 or more treatment levels or classifications, and it is analyzed by one-way analysis of variance, also called ANOVA. Here we have 3 factors, or 3 factor levels. It's different ways that we can train people on some skills. So the first one, self-study at a desk. Level 2 could be that they are lectured or shown how to do it. And the third way is to train them using a computer. So we have experimental units. We have 3 in each group. So 3 people are the experimental unit. We apply this treatment of how we're going to train them to each of them. And then our dependent variable is how long it takes them to be trained on that particular skill. So an ANOVA tests the equality of 2 or more populations, and it can be used on a randomized experimental design. Basically, we want to test, the test itself looks at, are all the means equal, and our alternative or research hypothesis are the means are not all equal. So as in the title, what we are doing is analyzing the variance between the groups. So we calculate out the total variation, the variation due to the treatment, and the variation due to randomness. In ANOVA, we are testing all the means at one time, whether they are all equal to 0. We use the F statistic for an ANOVA, similar to the Z-score and the T statistic that we used for 1 sample and 2 sample hypothesis testing. The F test comes from the F distribution, and you look the values up similar to what I showed you in the video last week. To look up the values, you'll need the degrees of freedom for the numerator and the degrees of freedom for the denominator, as well as the significance level. So that's what V1 and V2 are. So we're interested in the critical region on the right side of the F distribution. So we can reject the null hypothesis that all means are zero if the F value that we calculate out is higher than our predefined alpha critical range. So here's what an ANOVA table looks like and how to calculate out each of the values. But I can show you how to do ANOVA in Excel. It's pretty simple. If we have 3 treatment groups, let's say this is some of the other example where we're training them how to do a particular skill. And the first treatment is self-study from a book. Second one is we lecture them, and the third one is we teach them on a computer, and that's how long it takes them to learn this particular skill. So we have 3 treatment groups. We have how long it took each of them to learn the skill, and we can calculate analysis of variance, saying that basically our null hypothesis are that all the treatment methods are the same and produce the same results. So on the data analysis or the data tab, we go to data analysis and we take ANOVA single factor. We highlight our 3 columns of data. We have labels in the first row, and we're interested at an alpha of 0.05. Output it here, and it gives us our ANOVA table. So we have our sum of squares total, and our F value here. It calculates out p-value, and what we needed to see based on our results is a value higher than 4.2, but we only got 2.5. So our analysis does not support rejecting the null hypothesis, or we fail to reject the null hypothesis. And from our standpoint, none of the different methods has a significant difference in how we train someone on a new skill. So the assumptions for running an ANOVA are the samples are randomly selected, so always comes back to simple random sample or random sampling. They are all drawn from a normal distribution or approximately normal. And third, that all the variances are equal. Basic idea of ANOVA is that it compares 2 types of variation to test equality of means. The comparison basis is a ratio of variances. If treatment variation is significantly greater than the random variation, then means are not equal. So what our treatment variation is higher than some random effect that is going on in the data. Variation measures are obtained by partitioning the total variance. So total variance with the treatment variance and the random variance. The last thing I want to talk about is multiple comparisons. So the Tukey method is probably the most popular. So for each of these procedures, the risk of making a type 1 error applies to the comparisons of the treatment means in the experiment. Thus, the value of alpha selected is called an experiment-wise error rate, in contrast to a comparison-wise error rate. It tells which population means are significantly different. We run this test after we run the ANOVA, and that we have already rejected the null hypothesis. Tukey, like I said, is probably the most common, but there are 2 others that we'll talk about. The Bonferroni method is like the two-key procedure and can be applied when pairwise comparisons are of interest. However, the advantage of Bonferroni's method is it does not require equal sample sizes. The other one, called the Chef method, is developed a more general procedure for comparing all possible linear combinations of treatment means called contrast. Consequently, when making pairwise comparisons, the confidence intervals produced by Chef's method will generally be wider than Tukey or Bonferroni's confidence intervals. Okay.